Welcome back, Night Owls! And tonight, we're explaining where the magic absolute value bars pop up from when you're integrating 1 over x. Right? So if you look in the inside cover of most calculus textbooks and you say, what's the integral of 1 over x dx, they'll tell you it's natural log of absolute value of x. And the need for some rule when x is negative is apparent, right? You can't take the natural logarithm of a negative. But the function 1 over x, right, that does have values for negative values of x, so presumably you can integrate it. And in this video, I'll explain why we're allowed to just throw the absolute value bars on there. So we know that the derivative of natural log of x equals 1 over x, right? So typically, we'll just say, yeah, integral of 1 over x dx equals natural log of x plus c. This works when x is positive and the natural log graph actually exists there to begin with and can be differentiated to begin with to get 1 over x. But what about when x is negative? Again, textbooks will just say use natural log of absolute value of x. And we want to know, well, why are we just allowed to do that? So let's compare integral from 2 to 3 of 1 over x versus negative 3 to negative 2. I say negative 2 to negative 3 up here. It should be negative 3 to negative 2. So I know that the function 1 over x is an odd function. So by symmetry, I know this black area over here has to be perfectly matched by this red area over here. Right? However, when I take the integral, since the black area is above the curve and the red area is below the curve, so I know that my integral is actually going to be negative in this red region and positive in this black region. So I can say that integral from negative 3 to negative 2 of 1 over x dx equals the negative of integral from 2 to 3 of 1 over x dx. So that's going to equal the negative of natural log 3 minus natural log 2. That's going to get me natural log 2 minus natural log 3, right? When I distribute the negative sign, this one will become negative and that one will become positive. Notice, integral from negative 3 to negative 2 of 1 over x dx equals natural log of positive 2 minus natural log of positive 3. In other words, I can just take the absolute values here. It works in that case. And notice, there's nothing special about the numbers 2 and 3 that make this work. Any two positives, or if I integrate between those, if I integrate between the corresponding negatives, it'll also still work. The other case we'll want to look at is what if my range, or what if when I'm taking the integral, I start with a negative and end with a positive. So something like this. Let's integrate from negative 2 to positive 3. So now I subdivide my graph into this red region, this black region I had before, and this gray region, which represents the integral from 0 to 2. Now, informally, I can just say, well, the red region and the gray region are equal in size, but opposite in sign, so they cancel each other out. More formally, you'd have to use a process called, you'd have to go through a process for solving what's called improper integrals. Because you have a vertical asymptote at x equals 0, you can't actually just plain old take the integral there. You need to do more fancy stuff. Typically in Calculus 2 classes, this will show up briefly when you briefly learn about improper integrals. Then you'll stop talking about it. Then you'll have a unit exam that will have a brief mention of improper integrals, so you'll have to know it for that exam. Then you'll stop talking about it. Then your comprehensive final exam, it'll show up again, and typically it won't even show up after that, right? So this is a really nitpicky technicality that I'm about to go into, but might as well talk about it briefly. So what you would say is you take the limit as, instead of going from negative 2 all the way to positive 2, you'd go from negative 2 almost to 0. You go from negative 2 to negative epsilon, and then from positive epsilon to positive 2. Show that that always cancels no matter how close epsilon is to 0. And in the limit as epsilon goes to 0, it'll still cancel. But unless you're looking at the improper integral portion of your class, you don't need to worry about that technicality. You can just say, the red area cancels the gray area. Either way, once we cancel the red and the gray, that shows us that integral from negative 2 to positive 3 of 1 over x dx equals integral from 2 to 3 of 1 over x dx. And so that's still going to be natural log 3 minus natural log 2. I guess if your spare area were negative, then you'd say, okay, it's going to equal this negative area, which also equals the corresponding, which equals the negative of the corresponding positive area, just like we did before. And so what we find is, in all cases, no matter whether you're starting with a negative and ending with a negative, or starting with a negative and ending with a positive, clearly if you start with a positive, you also have to end with a positive, assuming your integral is set up properly and that your upper bound really is bigger than your lower bound. But no matter what, in each case, the absolute value rule still works. And so that's the formal justification for why it is that when we try to integrate 1 over x, we would say ln of x, but if x is negative, we can't take ln of x. Why are we allowed to do ln of absolute value of x? Because of this. Because no matter which case we're worried about, it always simplifies to something that is the same as integral of natural log of x from the upper bound to the lower bound, right? In this case, you're going negative 2 to positive 3, you get ln 3 minus ln 2. If you had negative 3 to negative 2, you'd still get ln 2 minus ln 3. I hope you found this useful, and as always, if you like the way I explain things and want to arrange private lessons, click the link in the description, and until next time, this is Dr. Nighttime wishing you a good night.